In 1965, Richard Feynman stood in front of a room full of the sharpest physicists on the planet and admitted something wild. He said nobody, not him, not Einstein, not a single living soul, actually understood the most important experiment in physics. 60 years on, mate, and here's the kicker, still nobody does. And here's the really mental part. This isn't some obscure equation scribbled on a blackboard. It's not black hole maths or string theory nonsense. It's an experiment so simple you could basically run it with a laser pointer and a bit of cardboard. But what it reveals about reality? It's enough to rattle the smartest blokes who've ever lived. G'day, I'm your host over at Curious Physics, and today we're cracking open the one mystery Feynman reckoned sits right at the heart of the universe, and why, 6 decades later, physics still has absolutely no clue what to do about it. Stick with me, because by the end of this video, you're going to look at the world completely differently. Alright, first things first. Who was this bloke? Richard Feynman wasn't your average physicist. Imagine someone who wins the Nobel Prize, helps build the atomic bomb, plays bongos in dodgy clubs for fun, and teaches physics like he's telling you a ripping yarn down at the pub. That was Feynman. He had this thing, a philosophy really, that if you couldn't explain something to a first-year uni student, you didn't actually understand it yourself. And Feynman, more than anyone, understood quantum mechanics. He literally rebuilt it from the ground up. He won the Nobel in 1965 for his work on QED, quantum electrodynamics, which is basically the theory of how light and matter interact. It's the most accurate theory in the history of science. We're talking predictions accurate to 11 decimal places. That's like measuring the distance from Sydney to Perth and being off by less than the width of a human hair. So when Feynman says something is a mystery, you should probably listen. And in 1965, right as he picked up that Nobel, he pointed at one experiment and said, paraphrasing here, that in this one experiment, you'll find the only real mystery of quantum mechanics. Every weird thing quantum physics does, it does because of this. The experiment? The double-slit experiment. Now, before you tune out thinking, oh yeah, I've heard of this one, hear me out. Because what most people get told is a watered-down version. The real story is way stranger. Right, let me set the scene. Picture this. You've got a wall with 2 thin slits cut into it. Behind that wall, you've got a screen. And you're going to shoot stuff at the slits and see what shows up on the screen. Classic schoolyard physics. Do it with tennis balls, which, fair enough, you'd have to hurl pretty hard to get through a slit. And you get exactly what your brain expects. 2 stripes on the screen, lined up with the 2 slits. Balls go through one slit or the other, end of story. Now swap the tennis balls for water waves. Do it in a ripple tank in your high school physics lab. Completely different deal. The waves hit the slits, bend around them, and on the other side you get this beautiful pattern. A bunch of stripes, alternating bright and dark. That's called an interference pattern. It happens because waves from one slit are overlapping with waves from the other slit, some lining up, some cancelling out. Basic wave physics. Waves interfere, particles don't. Got it? Good. Because here's where Feynman goes, hold my drink. What happens if you do the same experiment but with light? Well, light makes the interference pattern. Stripes all over the screen. So light must be a wave, right? For a while, that's what physicists reckoned. Problem solved. But then Einstein comes along in 1905 and shows that light also behaves like particles, little packets of energy called photons. He won his Nobel for that, not relativity. Wild, I know. So now we've got this confusing situation where light is both a wave and a particle, depending on how you look at it. Fine. Weird, but fine. Then someone asks a really dumb, really brilliant question. What happens if we do the double-slit experiment with actual particles, like electrons, tiny little bits of matter? You'd expect 2 stripes, right? tennis ball behaviour. That's what everyone expected. And when they ran the experiment, they got the stripes. But not two stripes, the full interference pattern, the wavy kind. Little bits of solid matter behaving like waves. And I know what you're thinking. Yeah, electrons are tiny, maybe they're bumping into each other and making the pattern. Good thinking. That's exactly what physicists thought too. So they slowed the whole thing down, way down. They set it up so only one electron gets fired at the wall every few seconds. One at a time. No way for electrons to interfere with each other because there's only ever one in flight. And you know what happened? One electron hits the screen. Tiny dot. Another electron. Another dot. Slowly, over thousands of electrons, the pattern builds up. And it's the interference pattern, the wavy stripes. From electrons fired one at a time, hours apart. Let that sink in. Each individual electron is somehow interfering with itself, as if the single electron is going through both slits at the same time, as if it's spread out like a wave until the instant it hits the screen, where it suddenly becomes a particle again and leaves a dot. Now, if that doesn't mess with your head, we need to check your pulse. But Feynman didn't stop there, because the next part is where it goes from weird to properly mental. Physicists thought, right, let's just watch what the electron is actually doing. Let's put a little detector at one of the slits and see which one the electron goes through. Simple enough, stick a camera in, watch the show. Except the moment you turn the detector on, the interference pattern vanishes. Gone. Disappears. You go back to two stripes. Tennis ball behaviour. The electron suddenly decides to act like a particle again, just because you're watching. Turn the detector off, the wavy pattern comes back. Turn it on, tennis balls. Off, waves. And I want you to really understand what this is saying. This isn't about the detector physically nudging the electron and mucking it up. They've tested that every way you can imagine. It's literally about whether information about which slit the electron went through exists in the universe. If it does, no interference. If it doesn't, full interference. Reality at its most fundamental level seems to care about whether anyone knows what's going on. Feynman looked at this and basically said, mate, this is the whole deal. Everything strange about quantum physics is hiding in this one experiment. Wave-particle weirdness, the observer effect, superposition, all of it, right here. And he said it in 1965. And 60 years later, we still don't have a proper answer for why nature does this. Quick reset. I know that's a lot to chew on, so let's zoom out for a second. Because here's the thing that blows most people's minds when they first hear it. We're not talking about bad measurements. We're not talking about our gear being too clunky to see what's really going on. This experiment has been run thousands of times in labs all over the world with every kind of particle you can throw at a wall. Electrons, photons, even whole molecules made of dozens of atoms. And every single time, the same mystery. So, physicists did what physicists do. They came up with explanations. Lots of them. And this is where Feynman's warning really bites. Because 60 years on, we still can't agree on which explanation is right. Explanation 1 is called the Copenhagen interpretation. Basically it says, shut up and calculate. The electron is in a superposition of going through both slits until it's observed, and then it collapses into one outcome. Don't ask why, don't ask how, just accept that the maths works. For most of the 20th century, this was the official answer. If you asked how the universe actually works underneath, you got told that's a philosophy question, not a physics one. Next up, the many worlds interpretation. This one goes, right, the electron doesn't collapse at all. It goes through both slits, and when you observe it, you split into two versions of yourself. One who saw it go left and one who saw it go right. Every quantum event spawns a new universe, which, I mean, it's elegant maths, but you're telling me there's a version of me right now who had Vegemite on toast for brekkie instead of cereal. Probably a few billion of them. Then there's Roger Penrose's idea, which is basically that gravity causes the collapse, and consciousness might play a role in how reality gets decided. That's the theory we unpacked in the consciousness video. Links down in the description if you missed it. And there are more. Pilot wave theory, objective collapse, cubism. Each one takes a swing at explaining the double-slit experiment, and each one has holes in it. And here's the punchline. After 60 years of seriously smart people working on this, we are no closer to knowing which one is right. The maths works. We can predict every outcome with 11 decimal place accuracy. We just have no bloody idea what the maths is actually describing. That's the mystery Feynman pointed to in 1965. It's not a problem we haven't solved yet. It's a problem we don't even know how to ask properly. And that's what makes it so wild. Because somewhere in that gap, between what we can calculate and what we can actually understand, is the real answer to how reality works. And it's sitting right there in an experiment simple enough to fit on your kitchen bench. All right, that's the rabbit hole for today. If your brain is a little bit scrambled right now, mate, welcome to the club. Feynman spent his whole life in that exact state. He used to say it wasn't about having the answers, it was about having the pleasure of finding things out. Next video, we're taking this same Feynman-style curiosity and pointing it somewhere properly terrifying. What actually happens if you fell into a black hole? Spoiler, the answer is weirder than any sci-fi film you've ever seen. Smash that subscribe button so you don't miss it. And do me a favor, drop a comment down below telling me which interpretation of the double-slit experiment you reckon is right. Copenhagen, many worlds, Penrose, or something else entirely. I read every single one. Cheers for hanging out with me. Stay curious, mate. See you in the next one.